Hi, this is Vivek. So somebody recently asked me on LinkedIn, Vivek, what's your favorite technique on trees? Now, out of this, everyone asking me about dev, how to do DSA, how to do CP. I thought this was a very interesting question because not a lot of people come and ask me, Vivek, what's your favorite idea on a certain topic? And for trees specifically, I think this is very unique. It is something called as Prufer code. I think you might not have heard about this because this is something that people only who do problem setting or who have solved good problems on tree generation have known about. But then this is such a powerful tool that can help you solve so many interesting idea related questions that it can be something that you can add to our arsenal, and it will actually come helpful on some day when some questions will require this for you, right? So we'll talk about that in this particular video. What is Prufer code and how you can use it to solve problems? Let's get started. Chalo ji, let's talk about Prufer codes. Okay, so let's start talking about Prufer codes. Now, Prufer codes are generally known for building random trees, right? So the first challenge that you can think of as an inspiration to learn about Prufer code would be, let's suppose you have n noded trees to be generated, right? So you have 1, 2, 3, 4 up till n, and you have to generate random trees of n size, let's say, right? How would you generate that? Now, generations are like topic in itself, and this is not an easy task. I mean, if you think about it directly, you might come to an idea which might look something like this. Hey, start with node number 1, right? And then initially there is only node number 1 by itself, totally independent. Now you have node number 2 to x being randomly added going forward. So whatever nodes have been added till now, randomly pick a node, add the next node as a branch of it. Pick one of these two randomly and add a node randomly. Pick one of these 3 randomly and add a new node randomly. Pick one of these 4 randomly and add a new node randomly. Pick one of these again and add a random node, right? And so on. So this keeps going on as long as you have n or don't have n nodes as such in the tree. And then once you're done, you have your tree ready. So this can be a very simple and direct idea that you can use to generate trees. But the problem with this particular idea is, hey, you have always 1 as root. Now what can you do with that? Maybe one thing you can think about is, after you generate the whole tree, like after you have this, maybe I will build a 1-to-1 mapping with a permutation of 1 to n, 1 to 6. What does that mean? 1, 2, 3, 4, 5, 6 will be renamed as, let's suppose, 2, 5, 1, 4, 6, and then 3 is left. And then replace these nodes, like 1 will become 2, right? This will become 2 basically. I'm just going to replace it directly over here. 2, this will become 5, this will become 1, this will become 4, this will become 6, this will become 3. So this is like a random node which no longer has 1 as its root, right? This is fine. But then there is another very big problem at its core. This idea itself is faulty in the sense that not every tree is equally likely. What does that mean, Vivek? So when you are generating trees this way, it's a good tree, but it's not the worst trees for many different test cases that might actually appear. I mean, if you are using these as test cases to test your tree, you might not get the worst performance on different algorithms. Why? Very simply, if you think about the height of this tree, that's not going to be very large, okay? So let's think about this being the core root node, right? And then I'm going to try and assume that maybe the worst kind of paths that exist is going to be something that diverges from the root itself. I mean, randomly it might occur over here also as the longest path basically, but for a randomly generated tree from the root itself, I'm going to assume that it's going to happen from there. You can prove it very similarly on either side too, when it happens in a child node. So when you have a situation like this, if you think about it, there is more nodes that are probable to be attached to this rather than any node to this, right? So when you think about it, the increase in heights are much more difficult. So let's suppose you have 5 nodes right now and the height is 2. Okay, so if you add one more node, so there are, let's suppose, 3 nodes, 4 nodes over here and something like this. So right now, if you randomly pick a node, the probability of height increase is very good because you have 4 nodes, right? But then now if you start taking random nodes out of this, what is your probability of increasing your height even further? Not really that high, right? Because it has to attach to exactly this. So you'll have to wait for these being extended first, and then you will get a chance that maybe randomly something over here will get extended, right? So if you do it this way, the height of the tree is like expected to be around log n. Okay, that's a result. I'm not going to prove it right now, but if you randomly keep taking the one branch that is extended and you keep extending it, it happens to be generate the largest like kind of path, but then that happens very low. That the likelihood of that is very low, right? So the average depth that you get is log n. So diameter would be around 2 log n worst case, right? So that's not a good tree to generate. So when people are generating test cases, if you are using this strategy to generate test cases, maybe some solution that works on some heuristics that maximum path length is not that large, they will actually pass your test cases. So in that case, you have to think about how you might decide and create test cases which works with even this. I mean, you cannot generate trees which are very short in depth, no? So how do you generate trees like that? And that's an interesting thing to think about. Right? This is where exactly Prufer codes comes into action. Prufer codes are the best tool when you have to generate trees, right? Labeled trees. Labeled trees means trees that have numbers on them. Now, what is Prufer code? Okay. So Prufer code basically says there is a strategy that you follow to generate a unique array for a tree. Okay. Prufer code for a tree is a unique array for a tree. So let's suppose this is a tree, right? What does Prufer code says? Find the smallest leaf of the given tree, let it be x, let the neighbor of x be y. Okay. Write down y on the piece of paper, like write down y next, then remove x from the tree. So find out a leaf, find out the smallest leaf, write its neighbor y, okay, because leaf will have only one neighbor, remove x from the tree, repeat this until only 2 nodes remain. You have got the Prufer code. Let's do it right now. What is the smallest leaf in this tree? So leaf over here are 5, 4, 3, 2. Smallest one is 2. Its neighbor. So leaf is 2, but its neighbor is 1. So you add the neighbor to the Prufer code. 1 is added to the Prufer code. You then delete the leaf 2. Now in this much of the graph, what is the next leaf? I feel 3 is the next smallest leaf available, right? So you add 3 neighbor to the Prufer code, that is 7, and then you delete 3. Okay. Now in this you have to find another leaf. So now 7 has become a leaf because this has got deleted. So this is now a leaf. Okay, because it has degree 1. What is the next like leaf? Maybe 4, but 4 has a neighbor that is 6. So we'll add 6 and delete 4. What is the next leaf? I think 7 and 5 are the only leaves available right now. 5 is of course lower in number. So 5's neighbor is 6. So you will add 6 and then delete 5. Now this much is the graph. What is the leaf now? 7 and 6. You take out the smallest one. 6 is the smallest one. You add its neighbor and then you delete it. Once you're done with only 2 nodes remaining, you will stop the procedure. So this is your Prufer code for this tree. 6717661. Now let's see, Vivek, this looks very random process. What are we doing? We are just pulling out leaves and adding it to the list. What are we exactly doing, right? It turns out that there is a unique mapping between this tree to this code. Okay, only this tree using this logic can generate this particular code, and from this code we can go back using this logic somehow and generate this tree too. So it's basically a one-to-one mapping between a tree and an array. So you basically just converted a tree into an array, a unique array. Now every tree has a unique array. That's another property of Prufer code. Okay. So if you see this beautiful code over here, which converts Prufer tree to a code, basically you have a bunch of edges and you have you basically build the adjacency list, but instead of list, it's adjacency set that you maintain a set over here. Now what you do is you go through edges. For every edge, you add the neighbors. This is standard graph creation. Then you have priority queue to maintain the leaves. So all the nodes that have degree 1 are leaves. So you add them to the leaves, but in negative sense, so that when you take out from priority queue, the standard C++ priority queue returns you the maximum. So if you do this, you will get the minimum. So now you want to build the Prufer code, which will be an array, and you want to do n minus, like if there are n number of nodes, or nodes number of nodes, you have nodes minus 2 number of elements. Why? Because over here we saw we were left with 2 more elements which we did not add over here. So we did it for n minus 2 number of elements. Okay. So you keep taking out one by one. You find out the smallest leaf. You find the neighbor of the leaf from that initial list. You add that to the Prufer code. When you delete that leaf, the neighbors, that neighbor that it had will no longer has this as a neighbor, right? So let's suppose there is X over here. So you go to X over here. X's neighbor is nothing but Y. So this is the neighbor of leaf. Okay. In the list of X, you will get Y, or that is to say set of X, you will get Y. So for leaf of Y, you find out, for this, you erase X. So you delete this H, right? This is what you're doing over here. And now if this has now a degree of 1, which means it's just only connected to one more node, then this becomes a new leaf. So add it to the set of leaves. This is what you keep doing again and again. If you think about it, if you just keep doing this again and again, it will maintain the set of leaves. This is a very nice way to maintain set of leaves, and you will get the Prufer code in sort of n log n, right? You will get in n log n. So this is just the same strategy that we talked about, and it converts a Prufer tree to code. But then this is only powerful when we have a reverse mechanism too. Like you have a code and you can convert it back to a tree. We can do that. Let's look into that too. Now this reverse conversion is actually a CSS problem, right? So there is this question called Prufer code, and this is the same thing written, that as long as there is at least 3 nodes, find leaf, find the smallest label, add the label of its only neighbor to the code and stuff like that. Now you are given a Prufer code of a tree, you have to find the original tree, right? This is also a question in itself. So after this video, you will be able to solve this question for sure. Okay, how do we solve this problem? And I'll share my code too, don't worry. But before that, let's try to understand how will we do this. So let's suppose this is the Prufer code given to us, and we have this graph over here, small graph, just to give us a hint that if we are building things correctly or not. But then this is the Prufer code. Now, let's try to think about the scenario over here, no? The things that are available over here, they are for sure not the leaves, because if it is over here, something of its neighbor, something that is its neighbor is a leaf. So it's very difficult to, of this being the immediate leaf being taken out first, no? So these cannot be the first element that was taken out, okay? So what we can do is we can maintain all the numbers. There were 7 nodes, we already know that, 1, 2, 3, 4, 5, 6, 7. We can maintain the frequency of them being present in this array. So 1 is present exactly once, 7 is present exactly once, 6 is present twice, rest are 0. Okay. Do you see a very interesting property over here between this graph and this over here? Okay. All those things which are 0 are actually leaves over here. Okay. This is actually a property of Prufer code. We will explore this in the next slide, but this is something that it actually boils down to. When you realize that when you are building Prufer code, the first time you're pulling out elements that are 0 in its frequency in Prufer code are the ones that are leaf. Okay. Right. So now when you have this scenario, you can easily find, you can maintain these 0 frequency wala elements in a set, and then you can pull out the smallest number that will be your first node. Okay. So there is this 2, which we know was attached to 1. So you build 2 to 1 edge. Okay. Then this 1 was attached to this 2. So you basically add it back over here, right? And 1 now. So what you do over here is 2 is attached to 1 for sure. And then 2 is now done out of this. You now don't care about 2 anymore. And then you think about going this forward, okay? You think about rest of the things. Now, 1 no longer has one of its neighbor. So 1 was present twice, no? Sorry, my mistake. 1 was present twice. So one of its neighbor has been deleted. So once one of its neighbor was deleted after this step. So the number of times 1 is now present in the rest of the code is 1. It decreases by 1. Till this much, 1 is present exactly once, right? Now for this much, it's again a Prufer code but on relabeled graph. Basically 2 has now been removed and there is a bunch of graph available somewhere, right? Which was a leaf. 2 was attached to a 1 node and 1 behaves like a new node that is attached to the rest of the graph, which are on the labels 1, 3, 4, 5, 6, 7. These are the rest of the things. And there is a Prufer code for that available. So it's like an incremental build if you think about it, okay? Now in this 7 is there, which is the smallest leaf with 0 degrees. 5 is over here, 3 is over here. So 3 is attached to 7 somehow. In this piece, there is a 7, which is attached to 3, and then that's fine, okay? And then since 3 is attached to 7, after this, sorry, not after this, when 3 is over here outside this, for this much portion of the like graph, we remove this, right? So 7 decreases by its frequency. So 7 is no longer has an attachment. Like this 3 has been removed when you have gone till this. So now 7 has 0. And then we are again thinking about which is the new leaf. So this has been deleted. Now you think about next, 4 is there. 4 is attached to 6. So there is a 6 over here somehow. 6 is attached to 4. 6 gets deleted. Its frequency becomes 1. 4 is now removed. Then 5 is there. 5 is also attached to 6 over here. Okay. And 5 is deleted. This moves forward. 6 frequency becomes 0, right? Now in this case, you have just 1 left. So over here, the smallest 0 frequency element is 6. So 6 is attached to 1. That is because till now everything else has been removed and the smallest node with 6 would have attached to 1. So it's 6 right now. So 6 should attach to 1. We are done. Now the only 2 elements left will have 0 degree, which means they are actually interconnected. You see, this is exactly the same graph we got. This is the procedure that we need to do. And you can do this very simply in code. The code is like few liners only, but the idea is you maintain the frequency of nodes being currently present in the Prufer code. And if you saw this very closely, there were a few very interesting observations. Okay. And we'll talk about them. One of them that I have not written down separately in slide, which because it's not required in any of the problems that we'll be taking forward. But Prufer code is actually incrementally built on the rest of the graph. I mean, if you think about it, once this node, the first node 1 over here, like whichever node it was connected to, 2 in this case, it's removed. It's like Prufer code for the rest of the graph, sort of, okay? Which you can use in some problem. But then for now, we don't need that, right? Let's think about the code. So this is like my, I think, AC submission for this code. This should be code to tree. What are we doing? We are finding out we are taking the Prufer code, we are taking the order, and then we are incrementing their frequency. We maintain the set of leaves, the nodes that are available as leaves, all those which has 0 frequency. Similarly, all those which had 0 frequency, we are maintaining them in leaf set. We are finding the smallest leaf available. We are erasing them as leaf. We know that they will be connected to the first node of the ith node, like first node, second node, third node, so on. And so we print that edge over here. And since that edge is now removed, I mean, we are building the Prufer code sort of, and that's how we are maintaining these edges. So the frequency now decreases for the rest of the graph. So now we have to incrementally find the rest for the rest of the Prufer code, how exactly, what were the edges. So we just delete this. And then if the frequency becomes 0, that node now becomes a new leaf. So we add it to the set of leaves. And then finally, the last 2 elements will be connected among them each other. Just like in this case, 1 and 7, we had to add this last edge when they become the last thing. Similarly, over here, we just add the last edge and you're done. Very simple few liner codes that can help you solve this problem. Right. So this is what like Prufer code actually is. Okay. But then the power of Prufer code is much beyond this. If you think about it, it's beyond what we just talked about. It's not just one-to-one mapping. You can generate now random trees as well. But there are a few more interesting properties if you have to learn more. Number 1, a node has degree d in graph implies it will have d minus 1 degree of frequency in the Prufer code. Okay. Why? See, this has 3 degrees. You have 2 ones. This has 3 degree, it has 2 occurrences. This has 2 degree, this has 1 occurrence. These have 1 occurrence, they have 0 occurrence in the Prufer code. Very nice observation, number 1. Number 2, obviously like an extension of this would be leaves never appear on Prufer code, right? So if you have to find the leaves of a tree whose Prufer code is given, like it's just the elements that are not present, right? Okay. So we talked about generating random trees. How will you now generate random trees? Very simple idea. Take a n by 2 size array. Okay. N minus 2 size array. That's the length of Prufer code for n node. For every element, randomly choose one element between 1 to n. For all of them individually, just random 1 to n, random 1 to n. Choose that. And you will generate random tree. Convert this Prufer code back to a tree. All of them will be unique, right? In fact, the number of like n nodes tree, like number of labeled n node trees, like how many n node trees exist, it's nothing but n to the power n minus 2. There are n minus 2 positions. Each has an option of n elements, 1 to n. You can have 1 till up to n. Remember, we can repeat elements also. So every element has an option to repeat, but you have 1 to n. For each element, you have choices up till n. There are n minus 2 elements. The number of trees that exists, okay, is nothing but n to the power n minus 2. Every Prufer code that you generate of n minus 2 length corresponds to a unique tree. That's another interesting property. Okay, this is called Cali's formula. If you want to read more about it, you can search for it. But basically, the number of labeled trees of n nodes is n to the power n minus 2. And now you know a way to generate random trees too, right? Now, another interesting like sequence or like derivative question that are created generally on this that you will see in competitive programming in general is you're given a tree, like let's suppose you have like degrees given to you, that how many trees exist with this degree sequence, that one node has 3 degree, one node has 2 degree, one node has 1 degree, one node has 1 degree, one node has 1 degree. And actually the answer is 3. Like you can see that 5 has 1 degree, 4 has 1 degree, like 3 has 1 degree in this case. Okay, so 5, 1, 5, 4, 3 are 1 degree nodes. 2 is 2 degree node. 3 is 1. 1 is 3 degree node. So you are given the degrees for each node. Tell me how many trees exist. Okay, and this is another beautiful application of Prufer code. Now we know that every tree of n size can be written in Prufer code. We also know another interesting property, that if these are the degrees, the number of times 1 will appear in the Prufer code is nothing but 2. Number of times 2 will appear is once, right? And then 3, 4, 5, they will appear 0 times. Why? Because d minus 1 times, okay? And Prufer code will be of 3 length, okay? And minus 2 length, right? So you have 2 times 1 present and 1 times 2 present. How many different codes can you create? 2 can be over here 1, 1. 1 can be over here 2, 1. 1, 1, 2. 3 codes. So 3 different trees. Each of these will correspond to one of them, right? Basically, this will correspond to this. This will correspond to this, and this will correspond to this, right? I'm basically thinking, in this case, the first leaf, 3 is attached to 2. In this case, 4 is attached to 2. In this case, 5 is attached to 2. That's what I'm thinking about. And then that's how I'm connecting it. Okay. So this is basically how you think about building Prufer codes. Okay. And not just building Prufer codes, you think about if your degrees are given, how do you think about Prufer code? Okay. In fact, you can generalize this, that you know that I degree has di formula, and it will be present di minus 1 times. So it's like n minus 2 positions, and you have to choose n, choose d1 minus 1, then n minus d1 minus 1, choose d1 minus 2. So just permute them. So basically there is d1 minus 1 number of ones d2 minus 2, d2 minus 1 number of times 2, and so on, the number of ways to create an array. And that is nothing but n minus 2 factorial divided by d1 minus 1 factorial, d2 minus 1 factorial, and so on. Right? That's the general combinatorial formula for that. This is the Prufer code, and it's actually such a beautiful idea. There are a lot of questions created on this, but I'll give you one follow-up task to read more after this particular video, since it's already so long. Number of ways to make a graph connected. So given there are k components, right now in the graph, so you're given a graph, let's suppose, okay, and there are n vertices and n images, and if you try to do a DFS on it, you will find out that there are k components in the graph. So what you need to find is the number of ways of adding k minus 1 edges such that it becomes connected again. There's a very beautiful formula for this. It's basically you find out the component sizes using DFS, and then you can do size 1 into size 2 into so on up till size k, and you will have like a new specific graph where you'll have to find n to the power k minus 2. Right? Read more about this particular formula. You will have very interesting idea that you will learn in this particular blog. Read more about this. This will be like a follow-up task. And then at the end of this CPU algorithm blog, you will have good questions to solve too. So go through them. But then this is all. Make sure that you solve the CACS problem and attach the link to that in description. If you enjoyed learning this, do give it a like and do subscribe to the channel if you haven't already done that. It just helps me a lot to push more such videos. Creating such videos are super hard, and I hope more people enjoy learning a little harder content like this. Right? So thanks for staying till this point, and see you all in the next such video again. Bye-bye.